So I think now we're ready to begin. So can everybody hear me?
Yes, I can.
Okay. Okay. So today is our kickoff speech of our HWE ComSoc ISAC-ETI webinar series, and we're very honored to have Dr. Peiying from Huawei as our first speaker. So I will first introduce a bit about Dr. Zhu. So Dr. Zhu is a Senior Vice President of Wireless Research and a Huawei Fellow and HWE Fellow. She is currently leading 5G and beyond wireless research in Huawei. The focus of her research is advanced wireless access technologies with more than 200 granted patents. She has been regularly giving talks and panel discussions on 5G vision, enabling technologies and standards. She served as guest editor for HWE Signal Processing Magazine special issue and HWE JSAC special issues. So she co-chaired various 5G workshops in HWE GlobalCon. She is actively involved in 3GPP and HWE 802 standards development. She's currently a Wi-Fi Alliance board member. So prior to joining Huawei in 2009, Dr. Zhu was a Nortel Fellow and the Director of Advanced Wireless Access Technology in the Nortel Wireless Technology Lab. She led the team and pioneered research and prototyping on MIMO FDM and multi-hop relay. Many of these technologies developed by the team have been adopted into LTE and 4G products. So I would like to also mention about our Q&A rules. So during the seminar, all of our audiences will be muted. And so if you have any questions, please type your question and directly send them to me. And we will collect the questions from both our audiences from Zoom and offsite live broadcasting. So during the Q&A session, so we will choose 3 to 5 questions to ask Dr. Zhu. Okay, so thanks and enjoy. And I will hand over to Dr. Zhu. Please go ahead and share your screen.
Okay, can you see the screen?
Yeah, I can.
Okay, thank you. Thank you, Professor Fan, for the introduction. And my name is Peiying. I can't see you, but I'm very happy to be able to give this first talk on the integrated sensing and communication. I want to thank IEEE ComSoc to organize such a webinar. This is a very interesting and hot topic right now, and also I truly believe this will be one of key features for 6G. So integrated sensing and communication is kind of a short named into ISAC or ESAC. I really like this name. It's kind of a bit sounds like Isaac Newton. So today, oh, wait a second. I will talk a few things. First, I will introduce give us some high-level introduction on the 6G vision. This just give you a background where the ISAC sits within the context of 6G. Then I will talk a little bit more details in terms of the opportunity we see with ISAC, and we followed by the challenges. Finally, I will talk a little bit on the Huawei's proof of concept activity related to ISAC. So for the 6G vision, actually it took four generation 40 years for us to be able to connect the people and connect the society. this is mainly driven by the mobile voice and mobile broadband communications. And starting with 5G, in addition to connected people, actually we started to connect the things. This opened the door to the vertical market, and we see the more and more vertical industry started using the 5G to enable its digital transformation. So we expected the mobile network will be transferred from the connected society to connected everything with the 5G. Then going forward with the advance of AI technologies, and we see more and more things actually become more intelligent. And currently, the model is that we collect the data and send it to a centralized cloud, and the cloud will do the learning and instruct the whatever the device to perform the actions. But with the popularization of this AI learning, we see the centralized learning model will not be able to scale. And also, given that the large amount of data need to be sent, so we end up need a huge amount of network capacity to enable such centralized learning scheme. So we envision that this kind of mechanism will be more involved toward, involved toward a distributed system. So that's why we think that 6G will actually become a platform to enable this connected intelligence. So make it a distributed learning environment. If we enable this device with sensing capability, then you also get the benefit of data collection with the same network. So that's why we think that the 6G, the two key things will be AI, like new services will be AI and the sensing. And the network basically will transfer from the connected people, connected things to the connected intelligence. And if we look at the previous generation, we see the frequency used by cellular system also moving from a lower frequency to mid frequency and high frequency. For the 6G, it's likely it goes even higher, maybe to the terahertz range. So this is actually also another motivation for the sensing. Okay. So what we see is the 6G will go far beyond the communications, and it will serve as a distributed neural network to provide the distributed learning and so on. And the key feature for this 6G is that first we will have a native AI support. So what do we mean by the native AI support is that currently we see even in 5G, we're using the machine learning features to optimize the system, optimize the network performance, and some operation of the operation and management of network. This kind of function, we call it AI for network. But going forward, we actually, as I mentioned before, we see that the network will be used to the distributed learning purpose, because the network elements, we envision network elements will have the capability the computing capability. So this is a function we called AI for network. So combining these two features together, that's what we meant the network native AI support. And for the second feature is networked sensor. So essentially, we utilize communication bandwidths and the signals to explore the environment, view the transmission, scattering, echo, and so on. So, so that's we essentially turn the cellular network into a networked sensor. So the third main feature is extreme connectivity. I'm having some problem with animation. The extreme connectivity is basically involved of the traditional communication connectivity functions. So we will have a higher data rate, larger capacity, maybe better reliability, low latency, and so on. So this will enable the much immersive multimedia communication and so on, and also enable some large scale the industrial digital transformation. Then the fourth feature is the integrated non-terrestrial network. So this this one is actually also we started in 5G. Currently, there are work ongoing, but we view that 6G will be integrate this system at the beginning, the design, versus like the current system, mainly using the terrestrial design to maybe adapt that to accommodate the non-terrestrial system. And also we see the new development for the very low orbit satellites. That's the I think the game changer for the non-terrestrial network. Of course, the non-terrestrial network is not just for the satellite. There's also drone and HAPS and so on. The fifth feature is that the native trustworthiness support. If we look at the vision of 6G, we are thinking to handle the large amount of data and handling the censored information, and those are very sensitive in terms of data privacy and so on. So we needed to design the network architecture from the beginning to make sure that we have the network architecture capable to conform the data compliance and any regulatory issue and respect the privacy and so on. And also we see the more and more entity will join the network operation cooperatively. So we need to kind of have a network architecture, have a better trust model and so on to allow the multi-party run the network together. Finally, the green and sustainability is one of the key things we need to consider in 6G. This should be really the guiding principle. So it not only we need to look at the power transmission efficiency for the data transmission, but we need to look at the total power consumption, including the computing power. So so that we make sure that we can not destroy this environment by consuming too much power, especially when we're dealing with the AI learning. This power consumption is actually a major issue. So put all these features together, we see a 6G system like this. We see we will have various different type of devices, and those devices will have the both communication and the sensing feature. So you can see even human will have maybe have embedded some chip, will be able to sense some kind of biological information. And we see you can wear a glass, so maybe you can see the different view beyond what your eye can see, or even see the behind what's the scene. And a car equipped with sensing, which can look at the surrounding and so on. And these sensed data will be sent via the wireless uplink to the base station, and the base station itself may also have the sensing capability. So in our diagram, we call the neural edge. This could be the combined base station and the mobile edge. Then this neural edge can do certain learning, or send the data to a neural center. Then the neural center will put the data together to do the learning. Of course, each of these nodes can do the learning itself, then send the learned results over the network instead of the raw data. So therefore, we have the distributed learning capability built into the system. Then the action is sent back via downlink, the inferring action, so that the device can perform whatever the action they need to perform. Meanwhile, of course, we still have the communication capability. So in terms of communication, we see it can also benefit from this sensing. You will see with today's haptile devices, we can already do certain communication with haptical information. So in the future, we see today's AR VR application will be combined with multi-sensory information, so that you can have more immersive and touching feeling type of communications. And of course, with this sensing can also combine the remote sensing capability from the satellite to allow the large scale sensing as well. So by combining these together, it's possible we can build a replica of the physical world in the cyberspace. So we can fusion these different worlds together. So if we look at the frequency spectrum, typically every generation will have some kind of main target frequency bands. Then they will introduce some higher bands, but usually it's not used widely. As an example, in 4G, we have we're mainly working on the bands below 6 gigahertz, but we also introduced the C-band in 4G times, and a few operators used it, but it's not that popular. But 5G, we move a higher frequency, and the C-band becomes the main global band. Then we also introduced the auxiliary band, like mmWave. There's some usage, but not that popular yet. Going forward to 6G, we see this trend will continue. We think that by the time beyond 2030, the mmWave band will be matured. The technology will be matured. So more and more base station will use that. Then we will add some higher band, maybe Terahertz as an auxiliary band. But Terahertz probably it's good for the short range communication and integrated sensing and imaging. This possibility even will go up to the optical visible light band for some short-range communications. And also there's a trend that every generation we use wider bandwidth. You look at the 2G to 5G. In general, it's 5 times bandwidth to use. So we expect that 6G will probably also follow this trend. So we need to look at some bandwidths around the 500 megahertz area. I don't know why there is some kind of line drawing on the screen. So it's possible we can find this kind of spectrum around the 10 gig area. Okay, do you guys see a line on the screen? The two
Yes, I
red
can see that. Yeah, I can see that.
Yeah, I don't know how that happened. And I
maybe you have enabled some I don't know.
I'm not sure how
can you
to-
just
how-
you use Control Z to retreat?
See? No, there's nothing. Wait. No idea. That's very strange. I don't know how to get rid of it.
So and maybe you let's share the screen again, or just
Stop sharing, then sharing again.
Yeah, you can share that again. Yeah, you can stop sharing and share again.
Okay, I'm sorry about this.
No worries.
Okay, so now seems gone. Okay, so if you look at the use case scenario for 6G, of course, every generation of the services also take more than a generation from its inception to the mature. It will take you typically 2 generations. We see the 4G start the mobile broadband, but really 5G continued mobile broadband offer. So we expect 6G will have the similar services. So whatever started in 5G, like massive machine type of communication, ultra reliability, low latency communication. These services will continue in 6G, but with better support, better capabilities. But every generation also introduce some new services. So we see the 2 new services are the AI as a service and the sensing as a service. Then, of course, we have the, I mentioned it before already, with the better connectivity, we will have the immersive human-centric communication, maybe more popularize AR, VR, and even holographics type of communication. We started a smart city and a smart life for this kind of application in 5G already, but we see with 6G, there's more and more use case will be enabled for this category of services. So like we see in the city, even the building were probably equipped with communication and the sensing capabilities, so that will be enable the intelligence maintenance and so on. And for the industry type of application, many features or use cases specified as Industrial 4.0 are already enabled by 5G. However, we see some more demanding use case will be enabled by 6G. Some example like the robots collaboratively working together on a complicated task, or robot and a human working jointly. This is called some type of a cobot. So those type of use case will be enabled probably by 6G. Then, of course, with the integrated non-terrestrial communication, then we will be able to provide the global coverage to have those type of use cases which are not feasible currently in the 5G. For example, we want to do some kind of a remote monitoring for the forest or some usage on the people, you know, on the ship and in the area where currently terrestrial network are not reachable. So I will maybe discuss a bit more on the ISAC-related use cases, and so that you can see the opportunity with sensing. So before we do that, I will discuss a bit on the what do we mean ISAC? Yeah. So there are many sensors. There's many sensing technologies existing in today's world. So what in our contents we are interested in IF sensing, basically utilize the communication signal for the sensing purpose. So we can classify this type of sensing into two categories. One is device-based, and the other one is device-free sensing. The difference is that for the device-based sensing, the target to be sensed is actually a registered network element. So like today's cellular positioning. The device is a part of the network, and we sense this device position. So this is a device-based sensing. Then for device-free sensing, so essentially we want to sense the a target which are not part of the network. So more for the environment sensing and object detection. So for ISAC, we aim to provide support for both of these sensing. So device-free sensing is kind of similar to the LiDAR, today's LiDAR. So in the LiDAR field, they have this so-called monostatic LiDAR, where the transmit and receive are co-located, and biostatic radar where the transmitter receiver are not co-located. So of course with the ISAC system, we can also have the co-located sensing and the non-co-located sensing, in the sense of the transmitter and the receiver can be at different places. We call it a distributed sensing. Yeah. So by doing so, because we use the cellular the communication signal at the same time for the sensing purposes. So we essentially turn a cellular into a networked sensor. And these basically open the door for the new functions to detect the object, to track the object, to recognize the object. And of course, localization is even the existing feature. And we can also do the imaging with Terahertz. We can do very high resolution imaging. So these can be offered as new services. Then on the other hand, we can also utilize this sensed information to help the communication, to do a better communication. For example, you can do the better cell planning, better beamforming, and channel acquisition, and so on. There are different levels for the integration, the sensing functionality, and the communication functionality, the lowest level, you can just simply share the spectrum or have two separate equipment and just take care of the coexistence issue. Then you go in further, we can share the hardware and share the baseband processing, and even share all the protocol and so on. Our aim is the highest level, the tighter integration, so that we can design basically a same system, so that they can mutually enhance the performance of sensing and communication. So that's why we use the word that integrated instead of you will see in the academia, there's also other term like a joint communication and sensing. Very often they're talking about the just two separate box leverage the information from the other. Yeah. So for the ISAC usage category, there are many long list of use cases you can think about it. So instead of list them all, we kind of look at it and classify them into four major categories. One is related to the high accuracy localization tracking. Then the second is related to the simultaneous imaging, mapping, and localization. The third one is related to augmented humans capability or human sense. The fourth one is gesture and activity recognition. So there is a paper actually written by Huawei colleagues. This is published in the first symposium on joint communication and sensing. You can check for the details if you're interested, but I will also explain further on the those use category. So as I mentioned, the cellular positioning is not new. It has this feature since like a second generation, but previously from second generation to the fourth generation, this positioning feature is mainly to satisfy the regulatory requirement. For example, you need the support for the emergency E911 call and so on. So it's not a type of service offered to the consumer or other customers. But starting from 5G, the positioning or localization is actually offered as services. And here you can show you some example. The commercial use cases show you 6 commercial use cases. You can look at them. Essentially, you can track your bike sharing and car communication for the assisted car driving, and some the tracking for the shipped goods, and also some type of augmented reality. You need a positioning to enable that, some delivery purpose, and so on. And also there is a study, a technical report specifies detailed use case scenario and also the requirement for each of this use case. Specifically, there's a separate report related to the vehicular type of communication in terms of the positioning accuracy and the availability, also some kind of positioning latency and so on. And we see the positioning feature is really for release 15 for NI is mainly for the regulatory aspect. Then 16 is a major feature to support this, and we now at the release 17 basically they have enhanced the feature to improve the industrial IoT type of support. And we also see the trend maybe going for further for the 5G evolution. We'll have a low power, high accuracy positioning support for indoor type of applications. So going forward toward 6G, the main thing is we see the high accuracy localization and tracking support to enable even further more applications. So currently we mainly aimed at the meter level accuracy. And however, I mean, the positioning accuracy. Some special case will have a higher accuracy. For 6G, we are targeted to the from meter level to centimeter level accuracy. With centimeter level accuracy, we can actually enable the maybe device level of placement, even module levels installation by the robots, or we can actually store things or fetch things in a tight space more accurately, and so on. So there's a list of application in those category. And in addition to those absolute localization, there is also high accuracy needs of relative localization. When we talk about the relative localization, we refer to two or more objects need to know their relative positioning. So this will enable some a fleet of drone to coordinating their flighting paths, or the drone docking onto the moving car and so on. And you can also imagine that we have these robots and or AGV cars, when they do the navigation, you need a relative positioning in order to go in slow, very tight spaces. Further, we with AI capability and the localization, we actually can move those absolute and relative localization towards semantic localization. Essentially, we can imagine a robotic waitress understand the command to deliver some drink to a certain table or certain customer. So essentially, he's able to localize the customer view by understanding the semantic and the localization jointly together. So we see the change for the positioning from today's device-based only to both device-based and device-free based. And the accuracy I mentioned already, and semantic localization I mentioned already. We also see the trend away from today's two-dimensional positioning capability move toward the multi-dimensional positioning capability. So the second category is related to the simultaneous imaging, mapping, and the localization. So there's already lots of work related to the simultaneous localization and mapping. So basically this utilize the positioning plus the mapping capability to mutually improve the mapping and localization performance. One of the key issue related to the cellular positioning is that the performance is bound by whether a device can see the multiple transmitter. In this case, typically you need a 3 base station sending the reference signal. So if a device cannot see receive 3 strong signals, then the accuracy of the positioning will decrease. But with SLAM, you can actually use the landmark or the environmental landmark information. Use that as a virtual anchor point, so to the improve the positioning accuracy. So this is the diagram actually is one of our research results to show that in the indoor environment, we're using some virtual anchor points to improve the positioning accuracy from traditional, we can only do 60 centimeter, but in this environment, and we improve it to the 10 centimeter. And we also show that if it's within the target and the object, it's now my device is within 10 meter, we can almost get to the accuracy on the 1 centimeter level. This you can look at the paper I mentioned before to see more details on this topic. With this feature, of course, we can do the 3D construction of the surroundings, and we can have high accuracy positioning even in the non-line of sight. So the second scenario is, of course, we can do the indoor imaging and mapping. This case is a very useful for us to do the indoor scene construction so that you can do the better navigation, and also you can use the outdoor imaging and mapping capability to build what we call a 4D city map. This 4D, the fourth dimension is in the time domain. So in addition to the X, Y, Z position. So this is very useful probably for the fully autonomous driving. And also it is very useful for the smart city services and smart delivery and so on. We see those type of capability will enable cars, robots, and the machine to be trained of almost have a human-like sensing capability. So if you put those together, plus we have the multi-level of network deployment ranging from the non-terrestrial to the macro cell system to the small cell system and so on, plus the collection of the device. So we can actually easily build a replicate of the physical world, like you can build a virtual city. You utilize this virtual replication information, you can do the city planning. So if you want to put a new building there or a new road there, you can do the environment study and or the traffic impact study and so on before you actually start the physical work. So with integrated sensing, there's one benefit is you can actually do this all day, and you can do it at night, which is unlikely. You can do this use the video camera, and you can do it in the bad weather, which also will not impact such capability. So you see, there's many advantages by leveraging the existing infrastructure. Of course, with the this virtual, city information, we can also help the cellular provider to have a better understanding where do they need to add a new base station, or they need to optimize their base station location and so on. Yeah. So the other category of the sensing is to augment the human's capability. So allow you see things beyond your eyes. For example, you can have a very high resolution viewing of objects. This is like almost you can have a wearable microscope type of glasses. This probably very useful in the remote surgery, the hospital, like diagnose certain diseases, and or even for the industrial environment. It's useful for looking at the defect of the product, and even you look at your leakage on your sink and so on. The second thing is that you can see things behind hidden surface, or you can see the hidden objects within a box or behind the wall, and so on. And you can look at things behind your skin, so you can even see your heartbeat and so on. Then the third category is the using the, especially with terahertz, you can do the spectrogram analysis by looking at the spectrogram. You can able to analyze the property of the some objects. So this way you can analyze the food you are eating to count how many calories you are consuming, and you can look at the air quality and like a PM 2.5 analysis. Of course, you can, in general, you can do the invite monitoring to monitor the pollution and so on. So there are also a long list of things we can do with this capability. And of course, the gesture and activity recognition, this is probably well understood, since Google is also quite, for a while, they have been promoting this using one of their project. So this is kind of a new contactless human-machine interface. So you can actually have this type of contactless control at a different level. Macro level, you can look at the people, whether they are falling onto the ground, or is there the intrusion, illegal intrusion to the home or to the hospital. You can also, for the rehabilitation, you can look at their, the actions and be able to correct them and so on. This is also useful for the sports and so. Then for the macro level, you can use your hand waving to control the lights, control the entertainment system, and even if you don't have a piano at home, you can do some type of a virtual piano playing with your finger wiggling. So combining with AI capability, you can easily see this the option, like the applications are really endless. So we will be able to build the future intelligent human and machine interaction system in both smart hospitals and smart homes. So this sounds like far-fetching, but in fact, it's not that far-fetching. We already have a standard group in the Wi-Fi. This is they started working on this type of standardization started last year. And we expect that the spec will be available by the end of 2024. You can see some of use case Wyland was discussing last year, related, very similar to what I mentioned before, but of course, given the nature of Wi-Fi system, they are typically focused on the more short range and indoor type of applications. But you can see one of the interesting use cases that to use Wi-Fi to detect a sneeze. This could be very useful for the today's environment to detect the whether this virus, not virus itself, but this sensor environment. So hopefully I have give you some rough idea on the opportunities for the ISAC. The opportunities is huge. This is just a small sample of the use cases. So next I will talk about the challenges to enable this. So first one, the first challenge is given that we have a huge number of use cases, how are we being able to define some use cases, narrow down the use cases which has realizable KPIs, and given the cost, power consumption, etc., given these constraints. And also these KPIs are quite different from the communication KPIs. So we need to understand those new KPIs, such as sensing accuracy, resolution, and even the detection of false alarm capability, probability, and so on. So that's the first thing we need to do. The second thing, we need to understand when we define these KPIs, there's actually this theoretical limitation for each setup. We need to fully understand this. So luckily we have some theoretical guidance related to the parameter sensing, such as Kramer-Urban or Pearson-Newman criteria. And regarding the sensing resolution, we also have the some guidance for the like a Rayleigh criteria or the RB diffraction limits. These can be used to guide you to know what's the ultimate limit of the resolution you can have. And for the spectrogram sensing, there's also some guideline, and same for the sequence design and so on. So here I just show you a few examples. Basically, you can calculate what kind of resolution, imaging resolution you can achieve with a different frequency and given the distance and the antenna aperture size. That's the top left, like this. So we will fix the antenna aperture size. You can see, of course, so the further away the resolution is lower, and higher frequency the resolution is better. And similarly, you can look at a different angle given the distance and what is the impact on the resolution with different aperture, antenna aperture, and different frequency and so on. So essentially, these are the theoretical bounds, and we cannot design system beyond these bounds. It has to be lower than this one. So this will give us some indication. And the second challenge is that for the today for the communication, we typically use the stochastic channel modeling mechanism to allow us to simulate the system performance and so on. This is in a way is easier for large scale simulation. There's lots of work done to simplify the simulation, reduce the simulation timing and so on. But for the sensing, the stochastic mechanism may not be applicable, especially for localization, positioning, and mapping and things, because this actually, the performance is heavily depending on the setting and environment. So more deterministic model maybe need to be studied, and we can see the ray tracing or measurement-based model may be useful. However, these have their own challenge in the sense it's the scenario dependent, not easily to be generalized, plus it's time consuming. And for the imaging, when we're talking about the looking at the size of the object, which is close to the wavelength, then all this method will not work. We may need to look at the computation of electromagnetic way. Anyway, in summary, basically, we have a task ahead of us. We need to standardize the channel model and even the evaluation methodology. Then, of course, if we want to do the joint design of the communication and sensing, we also need some theoretical framework allow us to optimize certain design. We can look at the communication and sensing in a more uniform fashion, in the sense for the communication we have IF signal and modulated by IF source, and this manipulation is basically embedded the data information, so that on the receiver we can get the transmitted data. On the other hand, for the sensing, so essentially we also have an IF signal, but the signal is manipulated by the medium. Then on the receiver side, looking at the signal and went through the median, then you can get the median information. So these, if you look at it this way, then you can use well understood the channel mutual information theory framework to kind of jointly look at these two aspects. The main difference is that for the sensing, the IF signal and the source are not co-located. So this is just a simple look at the problem, but we're hoping that people will look further to understand what is there a unified framework, theoretical framework, enable us to do some theoretical analysis of the trade-off between this design. Yeah. So there are some work already being done. Here are two examples showing one for looking at the device-free scenario, the benefit of integrated joint design and versus separate design or separate optimization. Then the other one is talking about the device-based sensing. What is performance look like? Both of them actually have an indication that joint design will perform better. And if you want to look at details, you can look at this paper. But there's also a very good survey paper recently published actually in April this year. This talking about the different category of the sensing and based on the different category, what are the fundamental performance limit and the trade-off and so on. But there's still a lot of work need to be done in this area. Then the fourth challenge is that actually how to design a integrated system from the system architecture. I mentioned there's many options. You can have a co-located design, non-co-located design, and so on. You can have cooperated sensing. So how we put together into a system, that is a wonderful challenge. And also how do we signal each other? How do we actually synchronize this information together and put them together into a system. So this is related to the procedure design. So these are more useful for the future need to standardize design. And of course, I mentioned that with sensing, you can also assist the communication. So our goal is that we want to add sensing into the communication system, but at the same time, so we want to minimize the impact, hopefully not impact the communication at all. ideally even can boost the communication performance. So there are a study already by looking okay, whether if I given the some sensing information, what kind of communication performance improvement we can get. But here the work very often is assuming some ideal sensing information you can obtain. So we need to study a bit further in this area. And also in terms of hardware, because we're looking at the shares hardware for the both sensing and communication. There are many hardware impairments for the transceiver chain. You can look at the sampling jitter, phase noise, and also the IQ mismatching and so on. Of course, given that typically communication size is small, we want to have a portable device and a cheaper device compared with traditional radar system. So we probably will go with the architecture of traditional communication hardware architecture, but we need to look at the impact on the sensing performance. There's some example, let's say sensing will need a full duplex capability, especially for the monostatic type of radar system. While we know the full duplex is challenging, like a research topic for communication for many years. Yeah. So we need to be able to have this kind of a functionality. Then the second example is that the sensing typically need to have the accumulation of the results coherent added together this way. I don't understand why they are doing this thing again. Okay, so anyway, so this will have a higher requirement to the synchronization and so on. Okay. So this the seventh challenge is that to enable the Terahertz communication itself is a big challenge. Now we see the FCC actually already granted some spectrum for the experimental for the Terahertz communication in 2019, and also ITU allocated a large amount of a spectrum for this purpose. So the spectrum is not an issue. The challenge is how we can actually make this practical. Yeah. So there's many problem-related device and so on. So of course, the sensing can be done using the not just terahertz. They can be done using the other frequency as well. You can use low frequency, millimeter wave, and so on. So, but we see the benefit to using the terahertz sensing. This left side talking about some benefit, especially for the portable devices, is related to the size and accuracy and so on. But in general, we compare them in terms of portability, whether it's easy to integrate with the communication and power efficiency and accuracy and safety. So you can see the diagram show you the there's pros and cons for each type of frequency band. So in addition to the challenges I mentioned before, there are other challenges related to the ISAC. If we do the collaborative sensing, then how do we fuse the data together? I mentioned before the privacy, security, safety is crucial. These are the crucial things we need to guarantee. So the network architecture, we need to look at this as well. And of course, we need to take care of the power consumption and with a limited size and a low cost issue. Yeah. So So there are lots of work ahead of us. So now I will just show you a few samples of Huawei's activity in this area. So first is we do the channel measurement on for the terahertz bandwidth, and here I will show you the path loss measurement. Fortunately for path loss, actually, the attenuation factor, the measurement we found is quite aligned with the millimeter wave results. So we did those indoor measurement, and this higher frequency at 200 gig area also are currently ongoing. Then we look at the multipath scenario. Of course, with terahertz, you will have less cluttering. So the typically line of sight or with maybe one multipath. That's of half of a scenario we look at this kind of cases. Then we are also looking at the penetration loss for the different materials. This is unfortunately the penetration loss is very severe in terahertz, so we need to have a solution to kind of alleviate this problem. And we are also looking at more material. This on the top left, just showing you a set of material we have measured. And we're also looking at the terahertz communication system at 220 gigahertz, and also the imaging system at both 140 and 220 gigahertz range. So we did the indoor type of communication test, which actually surprisingly we can do quite a long distance and at a quite high data rate. And for the imaging, we were able to get around the resolution around the 1 to 3 millimeter. So there is a paper coming will appear in the EU CNC meeting in June, which describe more details on this imaging system. You're welcome to look at that. I have the link there. So, so this is this prototype is actually trying to build a portable imaging system using the cell phone form factor. So one of the key issues is that to get a good imaging resolution, usually you need a large antenna actual size. But given the real estate restriction on the cell phone, we cannot do that. So the challenge is how do we design the system to be able to get the high resolution with limited antenna actual size. So we have some solution is basically we build a virtual aperture with a MIMO structure. On the left side, you can see we build a 4 transmit train and with a 16 receiver. And this effectively gave us a virtual aperture size of 64. Then we basically another mechanism to improve the aperture is by moving your cell phone to create a moving platform to enable this sparse scanning, which is this kind of a process are used by remote sensing. So, but of course, with sparse sensing with hand movement, then you need to have a good algorithm to be able to recover the image. So we also look at the different waveform to use for the prototype, and we look at the continuous waveform type, which typically used for radar. Then we look at the OFDM typically used for the communication. And we did some simulation on the performance of this PSF. We used 2 different waveform, and then we look at this peak side lobe ratio and all this the integrated side lobe ratio to look at the also the range and the close range performance. For the purpose of this close range imaging, actually we found OFDM is quite suitable for this purpose. So here's the this testing setup platform. Of course, we use a robotic arm to simulate the hand movement, for the not hand, the device, to move the device. Then we can control the sparsity, essentially by controlling this sparsity, then we kind of trade off the imaging quality versus the speed, because we want to be able to form imaging very fast, so this example show you if we use the for null sparsity, like this is what we call 100% for aperture scanning procedure. We can see a clear image. Then with our algorithm design and even with 50% sampling points, we will be able to still have a decent, very good quality image. So here I show you the wait. I show you a video. This is a Terahertz imaging video. You can see the robotic arm with the form factor of the handset trying to scan an object hidden within the box. Here it's just showing a metal logo. You can see actually the scanning does not take that long. This is a finished imaging. So we tested this system for various objects, and we can do around the 2 to 3 millimeter level of accuracy. So this is also another video to show you the high speed, ultra high speed communication. This is a testing in the outdoor in our Huawei Chengdu site. We have the the transmitter and the receiver set up on the rooftop. So we are able to transmit the data beyond the 200 gig. And the distances are close to 1 kilo, yeah. Okay, so in summary, basically, we think that ISAC is one of the key features for 6G, and there are 4 usage categories. And you can see the list of applications from sensing, and we see the many challenges, and of course this is also research opportunities. Here we list the some of them, not exhausted list. And our initial research and prototyping results are quite encouraging. For both Terahertz communication and the high accuracy imaging and sensing. So if you want to know more details, there's a book available right now in UK. This book we talk more on the use case analysis and requirement, and also the technology related to this ISAC. And it will be available for the other places probably in June. Okay. All right, I will stop the presentation here. It seems I'm a bit over time. Thank you for listening. I will be happy to answer any questions.
Okay, thank you, Dr. Zhu. Very wonderful presentation, very impressive. And I do have received a number of questions. So I would like to ask a first question in our chat box. So could you please introduce more about semantic localization?
Okay, semantic localization refers to the scenario where you actually want to understand both the semantic instruction, then be able to associate with the semantic instruction with the location. So that, for example, I can tell robots to say, deliver this string to fourth floor, second table. Is that right? So then they need to understand fourth floor, second table, and so they need to associate this with the actual positioning. So that's what we meant.
Okay, sounds very interesting. So there's another question from Professor Wei Yu. So Professor Wei Yu, I think you can ask Dr. Zhu directly, and I will unmute you. Hi.
Hi, Peiying. Wi-Fi versus cellular, how do you see the relative roles of each for sensing applications?
Sorry, can you repeat that question again?
Yeah, Wi-Fi versus cellular.
Oh,
how do you
okay.
see the relative roles of each for sensing applications?
Oh, okay. So I think Wi-Fi has its own limited application environment, because typically Wi-Fi is more deployed locally indoor, and they can cooperate, but they are less cooperative in that sense. So versus cellular, I think we can deploy both indoor and outdoor, and the spectrum and the collaboration is a lot more in terms of the Wi-Fi. So so we see they probably will provide complementary support, but currently the cellular Wi-Fi design for sensing is mainly they are not changing the Wi-Fi design, then trying to leveraging or maybe add or alter some kind of reference signal to enable some limited sensing capability. There's also people working on the totally like a passive radar type of application, just use ambient Wi-Fi or cellular transmission to detect the object. So this can be feasible as well, but we see the limited usage. But with the integrated sensing in the cellular system, I think the use case is much. We can use it like a lot more scenarios.
Okay, thank you very much. And another question is from Professor Andrew Zhang. So Andrew, I have unmuted you. So can you ask Dr. Zhu yourself? Hello, Andrew. Can you hear me? Yeah.
Okay. Thanks, Dr. Liu. So Dr. Zhu, very impressive this presentation. And I have a question on the Terahertz ISAC system. According to your presentation, it seems that Huawei has done a lot of great work and achieved a lot of results. Right? So in terms of Terahertz ISAC system, what do you think are the critical technical challenges?
Oh, there's actually a lot of challenges related to the Terahertz system. I mean, just as I mentioned, even the communication itself, we have to mainly the range is very short, so need to have the mechanism to be able to provide longer range. Let's say, you know, design the device for the power output, power efficiency, and the IF impairment is also severe, and the for the sensing, in particularly, we're looking for the terahertz, especially for the higher band. We're more looking on the short range communication and device sensing. Then, as I mentioned, the form factor is really one of issue. We don't have much real estate on the cell phone to put a large antenna array there, which is typically required for the high resolution, because the as I shown in one of the diagram, this resolution is totally depending on this aperture size. So you need a lot of new innovation to overcome this problem. You know, you can do the high resolution, but without increase the size or incur the additional cost and so on. So and when with handheld, there's also this motion problem. Is that if you wave your device too fast, your hand too shaky, and all these things, you need to have a good signal processing algorithm to compensate those kind of issues.
Yeah. Thanks, Dr. Zhu. Very comprehensive answer. In your talk, you mentioned you actually tried both OFDM and FMCW type of waveform for the terahertz ISAC system, right?
Mm-hmm.
Yeah. So have you ever thought about to use, for example, pulsed signals? Because as far as I can see, terahertz actually provides a very great platform for developing transmission system based on pulsed system. Because of the bandwidth, it's very wide, right? And so the transmission interval can be very small, so that we can avoid the requirement for full duplex by using pulsed communication system. And it's also has a very good compatibility with the traditional pulsed radar. So what's your opinion on this?
Yeah, we are actually looking at so what I showed here is really our early testing, you know, prototype proof of concept work, but in terms of actual terahertz research, we are looking at the different option for the waveform design, as you mentioned. Especially there's actually one of the other challenges related to terahertz is the A2D and D2A. We cannot afford to have very high resolution A2D and D2A, especially when the bandwidth is very wide. So we were looking at those type of waveform as well. You know, as you mentioned, this probably not necessarily a very high spectrum efficiency, you know, waveform like OFDM. But we haven't get to the stage where we are doing the prototyping yet. So in terms of research, yes, we are currently looking at the different options. And actually, by no means, I'm trying to convey the information that OFDM is a good choice. We're just showing you what we can do with the existing, you know, solutions. But I'm almost positive that we will have better solution than this.
Yeah, thanks.
And also, even just for communication, OFDM may not be suitable for the uplink, you know, especially both actually uplink, downlink. There's a PAPI issue. Yeah.
Yeah, thanks. That's all from me.
Thank you.
So I think we can have final two questions. So one question I think is very interesting. So would you please comment on future investigation direction of fundamental trade-off between sensing and communication?
Oh, from from our perspective, yeah. I think the purpose for us to have this fundamental trade-off theoretical studies to guide our design, so that we don't have to rely on the simulation to compare the different design. Especially as I mentioned that even for the simulation, we don't even have a good methodology to evaluate those joint system because it's very scenario dependent. So once we change a scenario, then the conclusion may be different. That's why yes. We're looking for this purpose. So in the sense, we hope that you can get some kind of theoretical framework, but taking into some more realistic assumption so that it will be useful for us. Yeah, that's from our selfish motivation.
Yeah, very good. So I think we can have a final question on the so what would be the right way to promote ISAC? Because so as we can see, there is a monostatic sensing and bistatic sensing or passive sensing in your introduction. So what would be the easier way or the more practical way to implement ISAC? Monostatic or bistatic?
I believe we need to have definitely all of these, especially given that we have the networked system. And we already have a cooperated communication capability. So, so the mono case is just a special case of the biostatic, but as I mentioned, the mono case, you might have you know, some interference issue. Of course, as Professor Andrew mentioned, that this other maybe with clever design we can alleviate this problem. But with a cooperative, there's also issues related to the synchronization. Especially like you look at today's cellular system, the positioning system, this wonderful problem is that if we use the time of a delay to manage the position, the clock accuracy is actually yes. bottleneck there. So this will also create the bottleneck for the cooperative sensing given the practical constraint of the hardware. Yeah.
Yes, indeed. Yeah. So I think that will be all.
People have at this stage of research, we hope that people can study all the scenarios so that yes. we have a better picture, not limited on this particular case.
Yeah. Indeed, in the future, I think all kinds of sensing methodologies should be considered, right? So in the future cellular network. Yeah, so I think that will be all for today's talk and the Q&A. So thank you again, Dr. Zhu, for giving us this wonderful speech. So we do hope that in the future you can attend our webinar series again. So I would like to, okay, so I would like to share my screen and introduce our next speaker. So our next speaker would be Professor Joseph Kell from Technical University of Berlin. So this will be on June the 1st. And so we will send you all the relevant information via our mailing list and our social media. So again, thanks for everyone for attending our seminar. And we do hope to meet you again in the coming seminars.
Thank you. Thank you all.
Thank you, Dr.
Bye.
Okay. Thank you, guys. Goodbye.